Jorge Vitório Pereira from IMPA. As you know, his mathematical interests are 1, holomorphic foliations, 2, so again, holomorphic foliations, 2, algebraic geometry, and 3, holomorphic foliations and algebraic geometry. As you are going to see now in his conference, foliations with trivial canonical class, please.
Okay, thank you. Thank you very much. First of all, I'd like to thank the organizers for putting together this nice meeting. I have to say that it has a therapeutical effect on me. For a long time, every time that I heard Brazil, Italy, some image came to my mind. And I think that after this week, I will be able to forget that. Okay? So I want to talk about foliations with trivial canonical class. As you'll see, it will be about holomorphic foliations, but I would like to briefly recall the general setup. So foliations, for those that are not used to them, are just the composition of spaces, varieties in general, smooth varieties, in disjoint subvarieties of the same dimension, which are put together locally as leaves of a book. They can be continuous, differentiable, analytic, holomorphic, measurable, and they came in various tastes. Okay? When at least differentiable, which will be always our case, they are locally defined by level sets of submersions. So if you want, these are just generalizations of fibrations, where now the fibers are no longer embedded, but only immersed. Okay? So this theory was created in the 40s by George Hebb, a student of Charles Erisman. And one of the original goals was to understand classical works of Painlevé on second-order differential equations. But as soon as the definitions were laid down, a lot of interest appeared on the field, and we saw a lot of progress in the 60s and 70s. Just to have a taste what the results of that time had, let me recall two very nice results, one by Heffliger, André Heffliger, which says that there is no codimension 1 foliation analytic on S3, and also a result by Novikov that every codimension 1 foliation on a free sphere has a compact leaves. So essentially, to prove these two results, there was a lot of ingenuity behind, but it had one key too, which is Poincaré Bendix on the plane. So at this beginning, in the 60s, 70s, foliations were studied as topological and dynamical objects. I will not review all the literature in the 60s, 70s because it's tremendous. There's a lot of different points of views, a lot of works, and I will not be able to do justice to them. So in the late 70s, people start to study the local theory of holomorphic foliations, while before people were mostly interested in smooth foliations. At this point, the focus by many of the people working in the local theory was around the singularities, because in the holomorphic context, you can deal and you can define singular foliations rather easily. And they had a very few motivations, different motivations. One came from the Hilbert-16th problem, bound the number of limit cycles of a polynomial vector field on R2. There is a work by Petrovsky-Landis which claimed a solution to this problem, and their approach involved complexifying the differential equation and studying the holomorphic foliation. There is also a lot of motivation coming from René Thon, then a proponent of singularity theory, and he made several conjectures on the field which asked for research. and also by generalization of classical results, most notably, perhaps, is the results on normal form of singularities due to Poincaré. Okay? And decades of 80s and 90s, we saw a lot of important advance. I don't want to enter in details, but just would like to mention how these groups, these 4 different groups, based on Russia, France, Brazil, and Mexico, contributed to the field. And we had a result by Mattei Mossu, giving a topological criteria for the existence of first integrals. This was a conjecture of answering a conjecture of Thon. There is a result by Camacho Saad about the existence of separatrix. There is the analytical classification of saddle nodes by Martinez Ramis, a very beautiful result involving the study of divergent series. There is this monumental work by Akkad and Ilyashenko independently about the finiteness of limit cycles for real polynomial differential equations, and there is also the work of Iocos and Perez Marco on the realization of singularities with prescribed holonomy. Anyway, people moved on and started to study global problems. I mean global problems, but problems about foliations on compact complex manifolds. I will highlight 2 results from the decade of 1990. One by Cervolins Neto, which classified foliations of codimension 1 on P3 of small degree, small meaning 2, because, and essentially 2 is the degree of the differential form defining the object. And also there is a result by Marco Brunella, who classifying smooth foliations on compact complex surfaces. Okay. When I was preparing the talk, I was pretending to give an unbiased, quick history of the subject until here, but then I realized that it was not unbiased, it was completely biased, and that's what essentially what I studied. More or less my path to arrive at this point. So even starting from late 70s, these holomorphic foliations appeared sporadically as tools to deal with problems of algebraic geometry. The first instance of this phenomena that I'm aware of is Bogomolov proofs of boundedness of curves of bounded genus. Curves of bounded genus, there's a genus missing here, on projective surface with positive seg cross. This is from 77. There is also the proof of the abundance conjecture for threefolds through Miyaoka's semi-positive theorem, which provides a sufficient condition in order to a foliation be uniruled, meaning the foliation contains a lot of rational curves inside its leaves. So this is really a major result. It's essentially generalizes to three dimensions, the classical Henriquez Kodaira classification of surfaces according to their Kodaira dimension. There is a proof by McQuillan of Green-Griffith's conjecture for projective surface with positive seg class, which follows roughly the same lines as Bogomolov's proof, but has to deal with a lot of more deep issues. And there is also a proof that disjoint smooth hypersurface on compact Kahler manifolds or on projective varieties having the same class, Stern class, have essentially the same topology. More precisely, they have finite coverings, finite tile coverings, which are diffeomorphic. So the results that I want to discuss somehow fits into this feeling that the foliations, or at least holomorphic foliations, should be viewed also as algebra geometric objects. So essentially, we should try to mimic the theory of varieties, which after all is just an example of foliation, a foliation with only one leaf, or if you want, a variety foliated by points. You can see two different ways. We should try to generalize the theory of varieties, of the algebraic varieties, to this context of foliations. I am not the first one to say that. There is a very nice quote. I forgot to bring it here, but it's due to Xinshan Shern, who says essentially that the same way that that algebraic varieties are generalized to Kahler varieties and general complex varieties, you can see a generalization of varieties as differential equations. You can see differential equations as generalization of varieties. So after this quick introduction, let me try to be a little bit more precise about the objects that I want to discuss. So let me start giving a definition of foliation. So when X is a projective manifold, don't be afraid of that if you're not from algebraic geometry. It's just a manifold, a complex manifold embedded in a projective space. Smooth foliation on X is just a subbundle of the tangent bundle of your variety with local sections closed under Lie bracket. So if we are in characteristic 0, then there is the classical Frobenius theorem that says that F is locally the relative tangent bundle of a fibration. This gives this picture that locally a foliation is defined by submersions. So we give names to these objects. So this tangent bundle is TF, and we call the quotient NF the normal bundle of the foliation. And the general philosophy, borrowed from the theory of varieties, is that numerical properties of these bundles, when I say numerical properties, I mean the degree of them on curves, how they intersect curves, and so on, should govern the geometry of the foliation. I will speak about singular foliation, so it's important to give a definition. So smooth foliations are very rare, especially when we are looking at compact complex manifolds. There is no smooth foliation on Pn, for instance. While singular foliations are rather trivial to build. You can build a lot of singular foliations on projective varieties. So singular foliation is we just weaken the condition. We no longer look at a subbundle, but we look at a subsheaf, a coherent subsheaf, meaning that I have a bundle such that the dimension of the fiber is generically constant, but it can change at some special loci, which is still integrable, closed under Lie bracket, and without apparent singularities. This is just a technical condition that I feel obliged to put here, but you don't have to worry about it. Anyway, we have the singular set, and by standard things, a singular set is a subset of codimension at least 2. So a singular foliation you can just think as a foliation on the complement of a closed analytic subset of codimension at least 2, and that's it. So, and the dimension of F is the dimension of TF, is the rank of TF, and the codimension is the rank of TX over TF. So now I can at least state precisely my problem is that I want to look at this canonical bundle, which will be the determinant of TF. Intuitively, it's rather easy to grasp its meaning. We are just looking at forms, holomorphic forms of top degree along leaves of the foliation. I don't care. I don't define how they intersect vectors transverse to the foliation, but I know how to evaluate these one forms of top degree on vectors tangent to the foliation. So this is the canonical bundle. It's the same canonical bundle of a variety. And exactly what I said. And what we want here, or at least I want to discuss results that goes towards this direction, describe the structure of foliations with numerical trivial canonical bundle when the first rational sharing class of TF is 0. Essentially, I'm assuming that this bundle is as close to trivial as topology can see. So I'm assuming that it's topologically trivial, essentially, up to finite index. Okay? So why I care about this? So before I recall the result, let me just say that the general philosophy of Morris theory says that these pieces, at least in the case of these guys, are the prototype of one of the basic pieces of a variety. If you want to believe in the abundance conjecture in any dimension, if you want to believe in Morris theory, that it holds, then these varieties with numerical Kodaira dimension 0, with Kodaira dimension 0, are somehow one of the building blocks of any arbitrary variety. And the prototype of varieties of Kodaira dimension 0 are varieties with kx trivial. The same things go here. If we want to believe that there is an analog of Kodaira of the Morris theory for foliations, this one would be the prototype for one of the basic building blocks of any possible foliation. But anyway, let's stop with the philosophy and let's see some concrete results. So let's discuss the case of foliation with just one leaf, the case of varieties. So there is this beautiful theorem by Bogomolov and Bouville from 75-83 that says that after a finite tile covering, X is a product of an abelian variety. It's just a torus, a compact complex torus, which is also projective. A Calabi-Yau manifold, which is a manifold which has no holomorphic form except of top degree, and it has dimension at least 3. Or a holomorphic symplectic manifold, which is a holomorphic symplectic manifold. It has a holomorphic 2 form such that the top power is nowhere 0. So this theorem itself has a very interesting history. Bogomolov at first in 74, he proved for an infinitesimal version of it. He provided a splitting of the tangent bundle that make you believe that this result would hold true. But the complete proof appeared only after a while in a work of Bouville, but because in the middle appeared the solution of Calabi's conjecture by Yau. It's essential too. Essentially, Bouville uses Yau's theorem to provide a metric and the variety, and the decompositions comes from the standard Dehaene decomposition theorem for metrics, essentially analyzing the holonomy. So it involves deep analysis. The current, according to the best of my knowledge, the only proof available of this result involves very deep analysis. Involves Yau's theorem. Requires Yau's theorem. So the case of smooth foliations of codimension 1 was treated by one of my very good collaborator, a very good friend, a collaborator, Frédéric Touzé. And he proved that after a finite tile covering, you arrive at a certain situation. I will not focus now to describing this now because I will have a more general result later on that will provide a more general version of this. And I have to point out that in the case of smooth projective freefolds, using Morris theory, Stéphane Drouel had the same result in 1999, 10 years before. So essentially, Touzé's argument also relies on Yau's theorem. He does differential geometry on the leaves. He puts a rich flat metric on the leaves and uses results by Gromov to understand the geometry of these leaves. It's a key step on the proof. There is also a work by Cerveau and Neto that I already mentioned, which can be, they do more than this, but in particular, they classify foliations on P3, now singular, with Kf equals 0. And unaware of this result by Cerveau and Neto, Polishuk, coming from a completely different direction, classified these foliations under the additional assumption that Sing F was particular. So he had a particular case of Cerveau-Lins Neto's theorem published 1 year after. Anyway, if you still need further motivation, besides all this Mori dream, we can also say that these holomorphic Poisson manifolds of co-rank K carry codimension Q foliations with numerically trivial tangent bundle. And these were the original motivation of Polishuk and Drouel. And this connects to a lot of things. For instance, from holomorphic Poisson manifolds, you can use deformation quantization to produce deformations associative deformations of the standard commutative algebra for holomorphic Poisson structures on Pn. So people from algebra also are interested in this object, and you can go on. It connects to a lot of things. Okay, so let me try to say what we were able to do in Codimension 1. I have to say that essentially we have complete results only in this case, but I think it's pretty much all that you can say in that case. Okay, so let F be a codimension 1 foliation with numerically trivial canonical bundle on a projective manifold X. So we have to consider two cases. The first thing is that for this condition, Kf trivial, to be really meaningful, you have to have some kind of control on the singularities. Already in the case of varieties, if you have arbitrarily bad singularities, it's not very clear birationally what the condition Kf numerically trivial means. So you have to look for a functorial definition of what good singularities are, and Morris theory provides that. This is canonical. This is the kind of singularities that you have to allow to have birational invariance of plurigenera, and once you impose that everything is fine. So we have first to deal with the case where they are not canonical, we have not natural singularities, and in this case the foliation is uniruled. What means that your foliation contains rational curves inside the leaves, and you can reduce to lower dimensions. So this is essentially somehow, they should not be here. They are artificially, they have numerically trivial canonical bundle artificially because they have bad singularities. So, but anyway, this reduced the problem to 1 dimension lower. Otherwise, we have to pass to a tile covering, a finite tile covering, and then we can say that Kf is not only numerically trivial, but it's actually trivial, and that we have one of the following descriptions for the foliation. So the manifold X itself is a product of an abelian variety with a projective manifold Y. This projective manifold has trivial canonical bundle. And F is just a linear foliation on the abelian variety, a linear foliation on a torus that I'm putting back to X. Or we have the following situation. We have a rationally connected manifold F, which means that I have a projective manifold which is covered by rational curves. Any 2 points can be connected by rational curves. And in this rational connected manifold, I have a foliation G. So let me draw a picture. So here I have F. Here I have F. And on this guy, I have this foliation G. I have a curve B, a variety B with numerically trivial canonical bundle, and I have a representation of the pi1 of B into the automorphisms of this foliation G. So I have automorphism acting here, and then I can just take the product of F and the universal covering of B. Consider on F times B tilde the foliation, the product foliation G times B, and I mod out by deck transformations on B and the representation on F. So I mod out by pi1 of B, where this action is just the action I described. So this is what we call, the people in dynamical systems call a suspension. And that's what we have. It's a suspension of a foliation on a rationally connected manifold. And there is a third possibility that the foliation is a locally trivial fibration by hypersurface with trivial canonical bundle. So let me say one thing more. We can be even more precise. We can say that F is toric. And that this foliation G is either something that respects the toric structure, or is a degeneration of that. But I will not enter in this level of details. Okay? So that's what we have. And let me just give a very rough outline of the proof, because somehow I think this proof explains why I like so much the subject. The thing is that the first case is when the variety, the ambient variety, is not uniruled. Because then the point is that we can use methods of analysis to prove that the foliation is smooth. Because essentially by some results, some deep results by Buxton, Demaille, Paul, Peternel, we have that the canonical bundle admits a singular metric with positive curvature. And doing integration by parts, we can prove that, essentially do integration by parts, we can prove that the foliation is smooth. We can produce some transverse form which will wedge with the form defined in the foliation, the wedge will be non-zero. So this is something that uses this deep result of analysis by Buxton, Demaille, Paul, Peternel, which is essentially a metric characterization of non-uniruled manifolds, or of uniruled manifolds, if you want, plus some standard techniques. Okay, so this essentially says that we can use Touzé classification. In particular, we can prove that the foliation after an Untitled cover is defined by a closed rational one form. As a matter of fact, only once we arrive at this situation, we can arrive at the more precise description before, and all we have to do is to work to achieve this. So to do that, in the case of uniruled varieties, we need two ideas. One idea is the following. When you study algebraic geometry, you have one particular property that is very surprising for those that come from differential topology or other fields. If you look at spaces of sub-objects, these are still algebraic varieties, are still countable union of algebraic varieties. If you look to the space of all submanifolds of a manifold, it's just a mess. Infinite dimensional, it's complicated, hard to put the hands on. But if you are in algebraic geometry, if you are in the algebraic category, or even the compact Kahler category, the subspaces, there is a space parameterizing subvarieties which is still a countable union of varieties. So this leaves a lot of ground to do things. And essentially, this hypothesis of canonical bundle 0, numerically 0, allow us to do the following. We start in our variety X, which is now uniruled, so it means that it has rational curves everywhere. And from our foliation that is on the space, we can produce a foliation on the space of rational curves. And this foliation is non-trivial, it's not the foliation by points, because of the hypothesis canonical 0. And we can work there, we can do things there, and conclude that our foliation is not still defined by a closed rational one form, but it's close enough. It's a foliation which we call transversely projective, which is somehow a generalization. Like closed rational one forms is something related to the abelian group, transversely affine is related to the affine group, and transversely projective is related to PS at 2C. I'm talking about the possible groups acting on a line, on C0. Okay? So we have that. We are there, but not yet. Another wonderful thing that you can do with algebraic varieties is essentially, because algebraic varieties are, of course, schemes, right? Schemes for constructions of on a geometric object starting from a certain rule. So these are algebraic varieties. They are defined by a finite number of differential equations. These are algebraic objects. They are defined by a finite number of equations. These equations have a finite number of coefficients. This finite number of coefficients define a field, define a ring, define a finitely generated Z algebra. And you can look at maximal ideas of this Z algebra, and you can mod out by then in order to produce objects in order fields, in fields of positive characteristic. And it's wonderful that geometry in positive characteristic has a lot to say to foliations. I'm not the first to observe that. Indeed, this goes back to the work of Miyaoka, and also to the work of Mori. This whole business of producing rational curves on varieties, there is no other way than reducing modulo P. And what we can do, and what happens, something that I observed already in my thesis, is that for codimension 1 foliations in positive characteristic are rather strange. They are very temperamental. Either they have infinitely many leaves through every point. This is the case algebraically integrable. It makes no sense to me, but that's like that. Or if they don't have, or they don't have a general leaf to they do not have a leaf to a general point, because to compute a leaf, you have to solve some differential equations, you have to solve some recurrence relation, and will appear factorial. Just look at the equation of the exponential, and you can't do that in characteristic P. But the foliation has some symmetries. And if they were in characteristic 0, they would be integrable. So doing this argument of reduction mod P, we achieve a certain dichotomy. Either we should suspect that they have rational first integrals in characteristic 0, or they are defined by a closed rational on forms. In the case that we suspect that they should have rational first integrals, in particular be defined by a closed rational on forms, we don't have much. Only thing that we have is a local control on the singularities. So we can say that they have singularities with a particular simple form. But in the other case, we have essentially what we want to conclude. And the point is that this holds for any possible foliation, and of course seems to be useless. But our hypothesis of canonical trivial makes this thing works. So in this case, we can lift back to characteristic 0 this closed rational 1 form that we produced in characteristic P. So of course, to do this argument work, you have to do for a lot of different P's and so on. So we put these two things together, coming from the two sides. The two arguments almost prove the theorem in full generality, but they do not arrive. But you put these two things together, and you can manage to arrive there. So essentially, that's how the proof goes. And to go there, to this case, it took something like 3 years to do this last step, to go to the precise description before. But it's not so hard. You have just to look in the right way. Okay? Okay. So let me say also something about these Poisson structures, right? So using these ideas, also with Loret and Touzé, so this theorem is a theorem with Loret and Touzé. And also using these ideas, we could recover Cerveau-Lins-Netos' theorem on P3 and generalize it to any Fano free folds with peak C. So this kind of penitence that we've made to go through all these particular cases, but it's rather instructive, and that's it. So this, again, there are people going through all these possible cases and constructing deformations of the polynomial algebra or of other things. So there is a very nice work by Brent Pinn, who builds deformations of the polynomial algebras following these Poisson's vectors on P3, these Poisson structures. Okay? And you can also look in the case of Poisson manifolds, there is also the case where you have only one leaf, but you do have singular set, which are the so-called log symplectic manifolds. Essentially, a symplectic structures are some, not exactly symplectic structures, but are structures defined by two forms with logarithmic poles which have maximal rank on the complement of the poles. So with one of my students, Renan Lima, we proved that log symplectic structures with normal crossing degeneracy divisor on Fano manifolds, any dimension, with rank 1 Pika group, are toric log symplectic structures on projective spaces. So this is still another characterization of a projective spaces if you want. I suspect that something like that should hold without this assumption, but there's some work to be done. I don't think that this is necessary. And of course, the conclusion would be that the manifold would be toric manifold. Okay. Okay. And what about higher codimensions? So we can, of course, treat the case of foliations of dimension 1. And in the particular case of foliations of dimension 1, it's essentially trivial. There's not much, not a lot of work to prove that after finite italic covering, they are defined by holomorphic vector fields. And since the work of Lieberman, holomorphic vector fields on compact Kahler manifolds are completely understood. The methods used to deal with codimension 1 are really codimension 1. It's very hard. Somehow we use that on dimension 1. You have only 3 possible Lie symmetries, Lie groups acting. Additive group, affine group, and projective group. And we use also in a lot of contexts. And so it's very hard, right? If you go from codimension 1 to higher codimension, I think that it's a constant in algebraic geometry, differential geometry, or whatever kind of geometry you're dealing with, it's hard. So we try to look at a particular case first to see what we can say. So we restrict to non-uniruled manifolds. So let's put away these uniruled manifolds. And we assume that not only the first Chern class, but also the second Chern class are 0 in cohomology. So in the case of varieties, again, using Yale's theorem, it's an exercise to prove that after finite covering, these are tori. So we expect to have something built on tori. So how the things goes? So we can prove in this case that TF is polystable, it's a technical condition, and that there exists a smooth condition, a smooth foliation transverse to F such that the tangent bundle of X splits. So for this, we don't need C2 equals 0, we only need C1. But from the polystability and C2 equals 0, we can use a theorem by Donaldson, Uhlenbeck, Yao, which says that the tangent bundle admits a flat Hermitian metric. So it comes from a representation on the unitary group. And we can study, and this is flat Hermitian metric, in those the transverse foliation. So it's in those the transverse foliation with a transversely Euclidean structure. So essentially, this is putting this flat Hermitian metric on TF is giving a Euclidean structure on the leaf space of F orthogonal. And together with Touze, we could prove that starting from these 2 conditions on a projective foliation, on a projective manifold, if X is not uniruled, then everything is smooth, the foliation is smooth, and the universal covering of X splits as a product of a power of C. So the leaves of the foliation F are covered by C, and Y. Y not necessarily compact, not necessarily projective. Complex manifold Y. Okay? So essentially, what we have to do is to, essentially the obstruction to have a product structure already in a finite level after a finite italic covering comes from the monodromy of this flat Hermitian metric. And what we can prove is that after passing to a finite italic covering, there exists a meromorphic fibration on X. Oh, sorry. Oh, I want to say one thing more. Here, already on this condition, when Tx equal to a sum of 2 subbundles, there is a conjecture of Bovid that predicts that the universal covering is a product. So essentially, we are setting this conjecture on this particular case, but we cannot do anything. In general, we need this transversely Euclidean structure. Okay? So, but we want more. We want to say something in a finite level. We don't want to go to a universal covering. So let F be a foliation as before, C1, C2 equals 0. Oh, here, a non-uniruled projective manifold. Then, after passing to a finite italic covering, what we can prove is that there exists a fibration by abelian varieties such that F is tangent to this fibration, and in its restriction to the general fiber is a linear foliation. So to do that, again, we are using all these wonderful properties of projective varieties. If you start with some representation, there is this thing called the Shafarevich map established by Kampan and Kahler, which produces a map for free, such that over the general fiber, the representation is finite. So this is something very particular, uses this property that the space of subvarieties of a variety is still a variety. We use the theorem by Zuo on the image of the Shafarevich map, which says that the image of the Shafarevich map, when the group is simple, we have to do a lot of reductions, but when the group is simple, non-abelian, then this thing is of general type, the image of general type. We use base properties of measure hyperbolicities and the fact that the leaves are, of course, parabolic as they are covered by Euclidean spaces. Okay? And we, for a long time, thought we could do better than this. We thought that we could essentially not have this meromorphic fibration. We could end up in a product, that X would be a product. But we learned from an example, adaptation of example due to faultings, that these things are not so simple. There exist projective manifolds of dimension 4, which carry a smooth, non-isotrivial fibration with abelian fourfolds with quaternion multiplication as fibers, and a codimension free foliation with vanishing Sharon class C1 and C2 equals 0, tangent to the fibers of F, and with leaves Zariski dense on the fibers of F. So it's really an example of the previous theorem says that you cannot go to a product because this fibration is not necessarily isotrivial. But if we restrict to codimension 2, there is not a lot of room to do funny things, and we can prove that indeed we have this product structure. It's a simple exercise on looking at the variation of the weight one polarized rod structure coming from the fibration by abelian varieties. Okay, so far that's all we can say for this problem. But I also have to say that now there are some new, already a while ago, but there are new motivations to look at these questions. There is a recent result by Grebe, Kebekus, and Peternel, which provides a generalization of Bogomolov-Boville decomposition for varieties with numerical, with Cadore dimension 0. So the minimal model will have tangent bundle, which is no longer bundle sheaf, but which splits as a sum of stable subbundles. And there is a lot of motivation now already to understand varieties to study this kind of problem in this more general setup. We have to go to varieties with canonical or terminal singularities, and we have to start to really embrace the possibilities of studying foliations on singular projective manifolds with canonical singularities. Okay, thank you.